Okay, I'm going to share my screen with you here. Okay, so we're chatting today about recursion. So the way I'm going to handle this is I'm going to actually use an example here. So I banged together two pieces of code yesterday, and I picked a particular problem that can very easily be done using recursion. And so I've done a program here that has it shows a standard way of doing this, and then I've written a recursive way of doing this. So and that is factorial. Okay, so I think we've done this before. We all know what factorial is. I've just picked a program that literally calculates 5 factorial. So here on the screen is the standard way we would do this. Okay, so this thing here, like I said, it just calculates 5 factorial. Okay, we've got our main method here. We should know that 5 factorial is 5 times 4 times 3 times 2 times 1. So as you can see, anybody that looks at that should see that that can be looped. Okay, so we're going to get some sort of looping algorithm here, and we're literally just going to, the easiest way, you could do it either way, it doesn't really matter. For me, I would do a countdown. Okay, so I would do a countdown for loop. So you can see I've just literally initialized a variable here, an integer, to just hold the running total. And then just for int x equals 5, x greater than or equal to 1, x minus minus. Okay, so it is going to be a countdown. And then I'm just saying factorial is equal to factorial times x. So factorial starts off as 1. So in the first loop, x is 5, 5 ones are 5. In the second loop, x is 4, 5 times 4 is 20. And then you get obviously times 3, and then times 2, and times 1. And then it just prints the output here. And you can see if we run the output, if I run it, 5 factorial is 120. Okay, if you can calculate on a calculator, you can do it in your head, it doesn't matter. We know that 5 factorial, 5 times 4 times 3 times 2 times 1 is 120. So this here is what we call an iterative algorithm. Okay, iterative, it iterates. Okay, it loops. So iteration means looping. So this is an iterative method for calculating factorial. Great. Let's go and have a look at, we can think of this problem in another way. Okay, so let's go to my recursive algorithm. Okay, so here is a recursive way of doing this. Okay, recursive meaning that we are going to write a method, and that method will keep calling itself. Okay, it's going to keep calling itself in order to calculate this. Now, how do we know what can be done as a recursive algorithm? Well, I can tell you now that there's a theorem that proves in computer science that all iterative looping algorithms can be written as a recursive algorithm. And the other side of that, all recursive algorithms can be written iteratively as well. So so each one if a looping algorithm, you can write it as a recursive algorithm. It does not matter, and that is a theory that holds true in computer science. It's proven to be true. There's not one algorithm that is iterative that cannot be recursive. It's just that sometimes we don't think recursively, and that's why we don't think of how to do this. So here we've got, you can see here by definition, okay, in line 10 over here, we've got that 5 factorial is 5 times 4 times 3 times 2 times 1. Now we can think of that as in a different way. Okay, we can say that 5 factorial is equal to 5 times 4 factorial. Think about that, because I can very easily just I can just do that. That's no problem. And what's in the brackets, 4 times 3 times 2 times 1, is 4 factorial. Okay. Same thing here. If I put brackets around there, then what's in the brackets there, 3 times 2 times 1, would be 3 factorial. So I can rewrite this. Okay, so this statement that I've got up top here, 5 times 4 times 3 times 2 times 1, I can rewrite it as 5 times 4 factorial. And we know by definition, mathematical definition, that 1 factorial is 1. Okay, you can take this to 0 factorial if you want to. By definition, 0 factorial is equal to 1 as well. I just take it to 1. You can take it all the way to 0. It doesn't really matter. You're just going to have 1 extra loop or 1 extra recursive call. So here's how this works. Okay, so remember, we are now using this fact here, the fact that I can take 5 factorial and I can write it as 5 times and then a reduced version of itself. Okay, I've now got 4 factorial. Now 4 factorial, I could rewrite that as 4 times 3 factorial, and so on and so on and so on until I get to 1. So here's how this works. Okay, so here's my main method. So I'm saying system out print line 5 factorial equals, and now I've written a small method here called factorial. It accepts an integer. Okay, so I'm going to feed an integer into it, and it returns an integer, the answer. So I call it factorial 5. So the first time I come into this method, the first time it gets called, x is 5. So it says if x equals 1, return 1. It's definitely not 1. We know it's 5. So it's going to run this part here. Okay, and it's going to return 5 times factorial. 5 minus 1 is 4. Now you can see factorial, the method itself, is calling itself in the return statement. It's referring back to itself. Now you think to yourself, immediately you think to yourself, oh my goodness, is this not going to end up in some sort of infinite loop? I'm just going to call myself. Sure. Think about, I don't know if any of you have used Open Broadcaster before. Normally when you start Open Broadcaster on your screen, it comes up, and inside there you get like a window of 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 a window, and it seems to go on to infinity. It's like a camera. If you face a camera in a mirror back at itself, you're going to get sort of an infinite number of images showing up. Similar sort of thing here. But the key is here, okay, is that I'm calling factorial, but I'm calling it on a lesser version of itself, okay? So this here, if x equals 1, that is known as the base case. That is the smallest. That's if we feed factorial 1. If we call factorial 1, the answer is 1. So that is the smallest case we can get to. Okay, so that is known as the base case. This is the recursive call. So we are returning x, which in this case, the first case was 5 times. Now it calls factorial 4. So it calls itself. Okay, so the next time it runs, x is 4, still not equal to 1. And we now get 4 times factorial 3. Okay, and then it calls itself again. And we get 3 times factorial 2. It calls itself again. We get 2 times factorial 1. Now, as soon as we get factorial 1, it calls itself again, but now we get an answer of 1. Now it can start unwinding. Okay, so it unwinds. So let me show you kind of what happened. So this here is a little bit of a representation about what happened. Okay, so in data structures, and it's very appropriate that I'm covering this now because this is a data structure. We get this thing called a stack. Okay, a stack is a data structure. It's a type of a list. Okay, so think of it as a one-dimensional array. Okay, it's a one-dimensional array, and we put stuff into it. Okay, it can grow to any size that we want. And your computer's got a stack in it. It uses them. It uses it all the time. I'll tell you outside of this video how it uses them. But you can think what a stack is. The characteristic of a stack is that what went into the stack last has to come out first. So think of taking an empty toilet roll holder. Okay, so or a paper towel holder, sort of a longish toilet roll holder, and you plonk it down on your desk. Okay, so the bottom is closed. You can't access the bottom, and you throw a ping pong ball in there, and you keep throwing ping pong balls in, right? So you throw a ping pong ball, throw another one, throw another one, throw another one. In order to get the ping pong balls out, you have to, the first ping pong ball that comes out is the last one that you put in. And it'll be like that all the way to the bottom. So this is called a LIFO, L-I-F-O, last in, first out type of data structure. And they call it a stack. So what's going to happen here is the first time we call factorial 5, this factorial method starts to run. It encounters this return statement. Now it's unable to return because it needs a calculation that it does not have the answer for yet. Okay, it doesn't know what factorial 4 is. It cannot resolve that right now. So what it does is it takes what it's done here and it pushes it. Okay, that's the techno term. You push something onto a stack and you pop it off. Okay, so it pushes this state onto the stack and it runs again. It creates another piece of memory for itself so it can run the second version. Okay, it gets to the end of it, factorial 4. It's unable to resolve that yet. Okay, so it pushes that on the stack. Okay, so we've now thrown another ping pong ball into the tube and it calls itself again. It's unable to resolve factorial 3. So it pushes that onto the stack and creates another version of itself in memory. So it popped another ping pong ball in, and it's going to keep doing that until it reaches the base case. Okay, as soon as X, the value that's passed in as a parameter, as soon as that is 1, we have an answer. It can resolve it. It returns 1. It doesn't return another factorial. It doesn't call itself again. We have hit the base case. So after 2 times factorial 1, when factorial 1 gets called, it generates an answer. There it is, 1. Okay. Now what can happen? The stack starts to unwind because now there was an answer here. 2 times factorial 1 has a solution. We know that factorial 1 is 1, so the solution is 2. Now that we know that, 3 times factorial 2 can be answered because it now plugs the 2 in and it gets 6. And it unwinds the stack again. It's now taking the ping pong balls out, okay, in the order that they were, in the reverse order to what we were put in. So now it can fill that 6 in, and now it gets 24. Now it's got to 24. It can now multiply that by 5 to give you the 120. So now the stack has unwound itself all the way to the beginning again, and it gets the result of 120. And I'll run this program, and you'll see there it runs. 120. So that is the key. The key to a recursive algorithm is it has to call a smaller version of itself heading towards the base case. Okay, and there's certain algorithms that lend itself so well to this. Another one would be finding Fibonacci numbers. Okay, you've probably heard of Fibonacci numbers in mathematics. If not, just look them up. It's a very, very simple thing. It's really just the sum of adjacent numbers in a series. You would have heard of the Fibonacci series. Something else that this is super handy for in computer science is what they call traversing a tree. So if you've got, say, for instance, a maze, okay, you've got a maze, and you are plotting the possible ways to solve that maze. Once I get to this here, I can go left and I can go right. Okay, and if I go left, I get a left and a right option down there as well. And you end up with like a tree structure if you draw it out. And you might want to find what is the shortest path on that tree once you've got all the possibilities in, because that will show you the shortest way to solve your maze. And you will use that in computer science. If you do computer science at university, I guarantee you will do traversal of trees. And recursive algorithms are the easiest way to do that. They really are very cool. So it's just really, recursion is just a different way of thinking about how you can calculate the answer that you want. And the fact is that we could take this 5 times 4 times 3 times 2 times 1, and we could rewrite it as a reduced version of itself, as 5 times 4 factorial. Okay, and then 4 factorial could be 4 times 3 factorial, etc., etc. Hopefully, you've got some sort of idea. Yes.
So I don't see how it will work with 0 factorial.
Oh, it won't. It won't. There's no. I did not cater for 0 factorial there at all. So what you would do is, if you're going to cater for 0 factorial, let me just share my screen up there again. Literally here, in this, at this point over here, you would have done this. Okay, you would have said else if x equals 0, return 1 there as well. Boom. Okay, so
yeah, I thought so.
So that there would take care of the case where it was 0. Yes, I've got no idiot proofing in this program at all. So I literally just put it in here just to sort of show you what recursion is. But yes, there is that other base case when if you put 0 factorial in, it must just return 1. Yeah.
Thank you, sir.
You're welcome.